It is time in our introductory videos of physics to jump into a revolution in physics. Newton's law of universal gravitation. Since you were born, you are constantly experiencing gravity. Unless, of course, you are an astronaut.
I really miss gravity. Can you drop something so I can watch it fall?
Yui, you're serious? Okay.
Oh, baby, you're killing me.
Our most primitive part of our brains has evolved intertwined with gravity, so that we take it for granted. But understanding gravity has captivated scientists and thinkers for millennia. It was Isaac Newton who, during the lockdown in the bubonic pandemic in 1664, used his time to nail down a brilliant description of gravity. He realized that the orbits of planets, but also the falling of an apple, could be explained through a force that depends on the mass of the object that experienced the attraction, but also depends on the distance between those objects. Newton's equation for the gravitational force between any two objects with mass says that the force of attraction is equal to a constant g times the product of the masses of both objects divided by the square of the distance between those objects. The negative sign indicates that the force is attractive, and the direction of that force goes from the center of one of the objects to the center of the other object. He used this equation to explain the trajectories of planets in the solar system and show that those trajectories are ellipses with the sun in one of the foci of that ellipse. But this equation can also explain the free falling of objects near the surface of the Earth. This is a universal law. This means that it applies to any two objects of any mass, no matter what the objects are made of, no matter how far they are. It applies to our solar system and to any planets in any far solar system. This equation has a constant, the constant of universal gravitation, g. Its value is 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. Look that this constant is really small, 10 to the negative 11. That is a very small number, and this explains why the gravitational attraction between two cars, for example, is negligible, hard to measure, and impossible to sense because of other forces acting on the two cars, for example. The force of attraction between two people of 100 kilograms at a distance of 1 meter is of the order of the micronewton, 1/1,000,000th of a newton. Unfortunately for Newton, he was not able to estimate this constant. It was Cavendish who did a delicate experiment more than 100 years later. Because of the universality of this law, we can apply it and use it to determine the masses of the Sun, for example, or the masses of other planets. Consider, for example, the Earth and the Moon. Let's estimate the mass of the Earth. We know that the Moon moves in an orbit that is very similar to a circle. Because of this motion, the Moon experiences a centripetal force. The centripetal force is the mass of the Moon times its velocity squared divided by the radius of its trajectory. But the centripetal force in this case is the gravitational force, the only force between those objects. Now we know the expression for the centripetal force. F is equals to g times mass of the Earth times mass of the Moon divided by the distance between the Moon and the Earth squared. Here we can cancel the mass of the Moon we can obtain the velocity of the Moon by dividing 2 pi r over the time it takes for the Moon to make one revolution around the Earth. This is about 27 days. We know that the average distance between the center of the Earth and the center of the Moon is of 380,000 kilometers. We can also solve for the mass of the Earth and put all these numbers into the equation to obtain that the mass of the Earth is of 5.97 times 10 to the power of 24 kilograms. And that is how you weight the Earth. May science be with you.